Welcome to Physics 2211, Lab 4, Oscillations. The first goal of this lab is to compare the predicted motion with the observed motion of a mass on a spring. The second goal is to plot the change in energies of the mass-spring-Earth system over time. In this experiment, we found that the predicted and observed motion show similar positions over time, with some deviations. The total change in energy of the system is zero throughout the observed time. Newton's second law states that the net force acting on an object is the change in momentum divided by the change in time. This equation is related to the velocity update formula, which in turn is related to the position update formula. The energy principle states that the total change in energy in a system equals the work done by the surrounding on a system and the transfer of thermal energy to the system from the surroundings. A system must be defined in order to determine the energies involved. A system with multiple interacting objects can include kinetic energy, potential energy, and thermal energy. The system consists of the Earth, the spring, and the mass. There are no external surroundings doing work on the system, so the total change in energy is zero. The total energy of the system includes kinetic energy, gravitational, potential energy, and spring potential energy. A free body diagram at static equilibrium shows the forces acting on the system, including the spring force and gravitational force. The oscillating motion of the mass on the spring was analyzed using tracker software. The position of the mass along the X and Y axis was recorded and stored in a table. The table data was converted into a CSV file for computational model analysis. The initial conditions for the model were obtained from the tracker analysis. The mass of the object was 0.402 kg. The time per frame was 0.095 seconds, and the initial position was derived from the tracker data. The spring constant K and relaxed length L0 were found using pre-lecture recorded videos 52. The equations for the spring constant and relaxed length were verified using mathematical derivations. The model incorporated equations for distance from relaxed length, energies involved, net forces, and updated formulas. The model compared the tracker analysis with the computed motion. The computational model generated an animation showing the oscillatory motion of the mass. Graphs displayed changing energies over time, such as potential energy components oscillating in opposite directions and the kinetic energy also oscillating. Position versus time graphs for both tracker data and model show some deviations, such as the Y position data shows greater discrepancies compared to X position data, and potential source of error could be unaccounted forces, inaccurate energy considerations, inconsistent marking of center of mass in the tracker. The change in total energy remains at zero, as shown by the sum of kinetic, gravitational potential, and spring potential energy changes. No work is done on the system by the surroundings, confirming the energy principle. The average oscillation periods were measured by analyzing X and Y position graphs. X position oscillation periods was 1.646 seconds, and the Y positions were 1.489 seconds. The difference in oscillation periods affects the calculations for the spring constant, spring force, and potential energy. Possible causes of discrepancies include drag forces and errors in tracker analysis. In conclusion, the computational model aligns closely with the observed motion but shows some deviations over time. The energy principle is satisfied as the total energy remains constant. Differences in oscillation periods along different axes highlights the impact of external forces and measurements in accuracy. Thank you for your time.